To the NSF Program Officer presentations, and I'll let Xiaowen Wang do the introductions.
Yes. Thanks very much, Tim. So, are we good?
Yeah, they can
on
hear
it,
you.
on it. All right. I think you're still morning time, Cheryl. How are you?
She's,
Muted?
she keeps dropping out.
Oh, really? Well, in the interest of time, perhaps we could start with Dan.
Yeah, I need to switch over. Yes.
Dan,
Okay.
Yes, can you hear me?
Yes.
Yeah.
yeah.
Sweet.
Okay.
Hello?
Yep.
Hello, so you're still morning time, Dan, right?
Just barely, yes.
Yeah. Well, thanks so much for doing this. As many of us know from last year's CyberGIS'13, the first international conference on CyberGIS space and time, Dan gave a fantastic talk there and mingled with our community as well. I don't think we need much introduction to Dan, who's a program director within the Division of Advanced Cyber Infrastructure. Now is moved from the Office of Cyber Infrastructure, used to be now as part of the Science Directorate. Dan's a program director of the software activities within NSF. Without further ado, Dan's your floor.
Okay, thank you. And just to confirm, you can see the title slide?
Yep.
Yes.
Yes?
Yes.
Or I'm not getting any feedback?
Yes, we can see it.
Okay, very good, thank you. All right, so this talk is a little bit similar to last year, hopefully a little bit different as well. But I'm going to start off maybe with what the same examples were, because I still think that they're actually quite good examples, and I'm going to assume that there are people that weren't at last year's meeting as well. So if we think about infrastructure in general and why infrastructure is important, we can think about how infrastructure relates to two different types of science. The big science projects, the large scientific challenges that are solved by often a single team, maybe with sub-teams working together. And an example of that is looking at hurricane forecasting and disaster planning. So when we think about this issue, we think about all the different things that need to happen in order to understand what's going to happen when a hurricane is approaching land. In this case, in the animation, Hurricane Katrina approaching New Orleans, where the dots are the set of forecasts from the location of the hurricane roughly every 6 hours. And so what you can see is that until the hurricane has gotten pretty close to New Orleans, it actually wasn't very clear where it was going to go. So really what that's showing is that there's a lot of different complex modeling that's happening here. There's atmospheric modeling, ocean modeling, coastal modeling, vegetation modeling, soil modeling, that are all coming together to figure out what's going to happen, with sensors and data as inputs into that process. And then once we understand where the hurricane is going, then there's a question about what's going to happen to the people. And so then we also need to have models of what people have built, where are the people at any given time of day, what are they going to do when they find out that a hurricane's coming. And so again, there's a set of data and models that are needed as inputs here. So the infrastructure that supports all of this simulation, is that initially there's some urgent processing, where we find out that a hurricane is coming, and we need to really start understanding what's going to happen. And other work that's going on, like high energy physics simulations, for example, temporarily become lower priority. And then after some period of time, we can kind of get into a cycle where we know that we're going to be getting wind forecasts from the National Hurricane Center every 6 hours, and we can start interfacing the urgent work along with the other work, and really still continuing to use the resources in the best way. So for all this to happen, there's workflows involved that actually make all the different models and all the different pieces go together. There's the software applications themselves that model all the different pieces. There's the networks that are needed to move everything around, the decision support systems, and the visualization that take the results and present it to people in a way that they can understand and make decisions based on, and data storage and interoperability. And so all of these things are parts of the infrastructure that NSF and ACI in particular are concerned with supporting and making sure that they're available and that we have the right things available to do the science at any given time. The other area of science, the other way of looking at science is looking at what's going on in the long scale. So this is the large numbers of researchers that are getting smaller grants, doing lots and lots of science. Actually, some interesting studies recently that seem to indicate that that these researchers actually do more science on a per dollar basis than the large science teams, but it's actually different as well, and we need to do both. But in any case, we have these groups of researchers that are getting small grants. And they may be a single PI and a graduate student, or maybe just a single PI or a single computational scientist. So they are specializing in something in their area of science. And they can't afford to also be experts necessarily in all the cyber infrastructure, all the software, all the networks, all the data. So the question and the challenge really for infrastructure in this case is to figure out what are the common and time-consuming processes and figure out how to automate them so that these scientists can, again, specialize in the science that they want to do and not have to understand all the details of the infrastructure, but be able to use that infrastructure stuff. And so a couple of examples of this, one is Globus Online, which is a data transfer tool, which was created with the idea of a web interface or a scripting interface where you say, I want to move this file or this bunch of files from here to here, and that's the end. You don't worry about the networks, you don't worry about the certificates, all that stuff is handled for you by the service. And another example is things like gateways, like NanoHub in nanoengineering, like Cypress and phylogenetics, that supply people with access to scientific software, and then hiding behind that software is high-performance computing systems, data storage systems, networks, identity management, maybe personalized project storage, things like that. So again, this is the other side of the infrastructure that NSF wants to support. So overall, the challenges that we have in infrastructure are that the teams of scientists are increasing in many ways in terms of size, in terms of disciplines, in terms of international aspects. Data is also increasing in a number of ways, size, complexity, the rates coming in. And as there's more and more data, there's need for more and more interoperability, and the interoperability happens both in terms of systems, so systems talk to each other, as well as policies that let the systems talk to each other, or let people get the data that's in some place, or let them import it into a model that wasn't originally designed for. The actual systems themselves that we compute on are changing, the number of cores is increasing, the number of types of architectures are increasing, the levels of memory hierarchy are increasing. Because some things are increasing faster than others, the balances are changing. So, for example, bandwidths are easy to increase, latencies are very hard to increase. And so, when you look at network, when you look at disk, when you look at memory, all of those things have different balances of latency versus bandwidth than they did 5 years ago. We also have changing limits. So we used to build HPC systems based on what we could afford to build. And now we build them perhaps based on what we can afford to power over the time that they're going to be operational. The system architectures themselves are changing, and the business models of how we use them are changing. So there's an increased role of clouds in science, and exactly how that impacts various fields really varies. The network capacity is also growing, so we have more and more things that are being put on networks, again, data, computing, sensors. And as those things are increasingly being put on the networks, we have an increased need for security on those networks as well. As I was mentioning earlier, software is a challenge. We have more and more types of physics and types of simulation that need to be included. We have new frameworks that try to include more things. We have issues about programming models and abstractions for both science and hardware, as well as for data, that probably aren't what we need to have in 5 or 10 years. We have issues about verification and validation, about reproducibility and fault tolerance, again, that are all often handled by software, or software is expected to try to figure out how to do it. And then finally, we have issues related to people. So we have issues about how people are educated and trained in using cyber infrastructure and building cyber infrastructure, and what universities and other research centers offer as career paths for those people, so that once we train them, we can keep them in science careers and not use them to industry or other areas. and how we give them credit and how we attribute the work that they've done, whether it's creating software, building data, or even building computer systems. So overall, I've kind of hinted at this, but I just wanted to define cyber infrastructure using this definition from Craig Storage in Indiana. That cyber infrastructure consists of computing systems, data storage systems, advanced instruments, and data repositories, visualization environments, and people, all linked together by software and high-performance networks to improve research productivity and enable breakthroughs not otherwise possible. So we can think of cyber infrastructure as being made of a number of elements, and those elements then have to have some way that they fit together. They work with other parts of the cyber infrastructure. They have to have some developers, individuals or groups, perhaps international. They have to be developed for a particular purpose and used by a particular community. And so when we think about infrastructure elements, we try to think about what the answers are to all of those individual points. So software, as I mentioned, is a key part of infrastructure. It sits in between the science and the computing infrastructure on the bottom, the computing hardware. It's the thing that takes the technological innovations and really turns them into scientific discovery. Or if you want to look at it the other way around, when you're thinking about discoveries that need to be made, it's the way that you figure out what technological innovations are needed in order to make that happen. It's important in education as well. As we're moving forward, a lot of education relies on software, and we have to educate people both how to use software and how to build software. So overall, I would say that science is really relying more and more on software, including services, not just things that you download, but things that you use remotely, in order to really get new discoveries made. I guess this is about a year ago when I was looking at a few different issues of science. It looked like about half of the papers were software-intensive projects. And NSF as a whole is doing significant software development across a bunch of different areas, and this isn't just NSF, it's also DOE, and really all the other federal agencies and international agencies that sponsor research. There's a wide range of software types, from systems to applications to modeling to science gateways, data analysis, algorithms, middleware, libraries. For all of these, developing and producing them and maintaining them are people intensive. And software lifetimes are often long compared to hardware, which means that the investments that we make in software really are things that we want to make sure are going to actually live over multiple generations of hardware and maybe multiple generations of science questions. And finally, software has what is often an underappreciated value, but I'm sure not by this. So NSF, a number of years ago, put together what is called the Cyber Infrastructure Framework for 21st Century Science and Engineering, or CIP21, as a cross-NSF portfolio of activities to really integrate cyber resources and to enable new science to be done. The ACCI, the Advisory Committee for Cyber Infrastructure, set up 6 task forces to look at different issues. These task forces had an NSF participant, but they were really community task forces led by a member of the community with almost all community members in them. And as you can see, these looked at campus bridging, cyber learning and workforce development, data and visualization, grand challenges, high-performance computing, and software. And after all these reports were made, NSF internally then started creating vision and strategy reports in these different areas for how we would look at these things. So ACI here is Advanced Computing Infrastructure. This is different than the ACI division that now exists. It's an unfortunate name collision. Software is the area that I'm most interested in myself and that I'm responsible for in ACI, the other ACI. And data is another example where we have a public vision and strategy report. In terms of software, we've gone a step further and created a document that we call Implementation of the Software Vision. And the intent of that is really to explain to the community not just what our vision is, but how we're actually trying to meet it, what programs we have and how they interact, and what people that are interested in proposing software should be looking at for different goals. If your goal is to produce software for a piece of infrastructure, for example, then you'd be looking at the SI2 program. If it's to try out something in science and engineering for a particular science problem, it might be the computational data science, computational and data-enabled science and engineering program, or something else. So if we look at the vision overall, it says that NSF will be taking a leadership role in providing software as enabling infrastructure and in promoting software as an important component of the 621 vision. We're going to advance the use and development of new software and promote the ubiquitous integration of scientific software across all disciplines. And so if we think about how we're actually doing this, we can think of 5 elements that go together. And the central element is that we want to create and maintain a software ecosystem that provides the capabilities needed to advance and accelerate science. In order to do that, we need to have foundational research that's continually happening, and the successful things that are happening in there need to be then pushed into the ecosystem and made available to the community. And then we need to have ways that we ensure that the community actually uses the things in the ecosystem in order to really do the science and engineering. And so this might be encouragement, it might be supportive people, it might be other things. We also have a number of policy issues that need to be brought into this. So there's policy issues, as I mentioned before, about academic culture, open dissemination and use, reproducibility and trust, curation, sustainability, governance, citation, stewardship, and attribution. And in all these areas, we need to, we being NSF and we being the community, really need to advance to make sure that the science is used, that the software is used as well as possible to do the most science that we can. And then finally, there's the education piece, which I mentioned before, where again, we're using the software ecosystem to train people, and we're training people to develop the next generation of software ecosystem. So within ACI, as I was saying previously, we have different activities for different types of software. An example is the XPS program, which is working with the rest of SCI's to do foundational groundbreaking research in parallel and distributed computing. I would say that really almost all areas of NSF have some kind of foundational research that happens in their core programs that often leads to software. Once those foundational research projects have been done, then it's often the next step is to test them.
Dan, we lost you for a minute.
Or answering a particular science problem. And within to prove that they can be used to make science and engineering breakthroughs. And then finally, once we have software that really is proven, the SI2 program comes in.
I guess. I don't think it's anything. I think it's our network.
Dan, can you hear us?
Try to take those innovations and turn them into sustainable software. We have software elements, which are, yes?
Sorry, on the last slide,
Yes, I hear you.
okay, on the last slide, not the current one, the last slide, the second item for your topic, the network is not behaving.
Okay, is this back now?
Not fully yet. It hasn't loaded. The slide hasn't loaded yet.
You hear me again? Hello?
Yes, we can hear you.
Okay, but do you see the presentation as well?
Not yet.
Okay, I'm not sure if you're speaking.
Your voice isn't any better than mine.
I know, but you need to give him some assurance.
Not yet. We're not hearing you.
Okay, so I'm not hearing you guys. I'm not sure what. Sorry, I'm not.
You're in the chat window.
Yeah.
Okay, you can hear me now, yes?
Yes. Yeah. it's not showing the right chat. I've got something to bring up.
Okay, sorry, so if I look at the presentation, unfortunately, I can't actually see you and I can't see what you're seeing, and I can't see the chat window that Mary's typing into. So if there's an issue, then please tell me that there's an issue in some way that I can hear, because otherwise I don't actually, okay. So let me go back to this, and if this is not working, then somebody please say something, and otherwise I'll assume that it is.
Software infrastructure.
And so talking about the different types of software that we're supporting in the SI2 program,
Still continue.
we have software elements, which are small 1 to 2 person projects, building specific software for a particular purpose. We have software frameworks, which are larger projects trying to integrate perhaps multiple elements, maybe up to 5 PIs, up to 5 years. And we have software institutes, which we're really just starting out on the process of trying to figure out what these are and how they're going to work. As we go across the spectrum, we have larger and larger communities being impacted, and we want to make sure that the software in all of these cases is really reusable. So we funded a total of about 75 projects that we funded at this point, and the URL that's down at the bottom is a list of all those projects, pretty much being updated almost daily at this point because a number of the recent ones are just starting to happen. And we also have institutes, which we funded again a set of 13 conceptualization awards. And these projects are now trying to figure out exactly how it would work. And we hope that we'll, in late FY14, that offers some of them a chance to become full institutes and to actually do some work. So the process that we use for actually going through these solicitations and decisions is that we have a cross-NSF software working group with members from all directorates, including Cheryl from SBE, who will be speaking next. That group has determined how SI2 fits with the other NSF programs, and again, this is where this implementation of the NSF software vision document comes out. We talk about solicitations and determine who's going to participate in each. We discuss and participate together in the review process, and then we work together to fund worthy proposals. And so what I end up doing really is matchmaking once we have proposals that review well, which means that I want to find program officers with funds and convince them that they should spend their funds on these proposals. And if we have a single disciplinary, a unidisciplinary project, like a bioinformatics application, this is pretty easy that I can work with a program officer in that area, and that program officer either likes the proposal or doesn't. If they like it, we can fund it. If they don't like it, we don't fund it. And likes it here really means that they feel like it's going to impact their community in terms of the research they can do based on the reviews and based on their knowledge of the community. If we have multidisciplinary projects, something like molecular dynamics that are used perhaps in some biofields, in chemistry, and material science, and engineering, then I try to work with a bunch of different program officers and build up a coalition of people that are interested in this project. And again, hopefully to fund the project. And for omnidisciplinary projects, which really apply to all disciplines like a web server or a math library, I will try to work with all program officers, but often the feedback that I get is that this is the responsibility of ACI. And so then we make decisions about funding these based on the peer reviewers and what we think they're saying about the impact of these projects on a variety of communities. In all of these cases, we need to be able to forecast impact of these projects. And we often do this by looking at past performance. So if we have a project in bioinformatics that has a user community, we assume that that user community is satisfied and that they're going to keep using it. If we have a new project that's just starting out, then it's very hard to try to figure out, is this project really going to be used and going to be useful to do research? So this is a question that we really try hard to answer. And when we get proposals that help us answer it, then that's much better. So I'm going to try to end here with a number of software questions for people that are developing projects. And by that, I'm going to start by saying that sustainability is one of the issues that we worry about. And sustainability to me means how are you going to keep supporting your software when I finish paying for it? And so this is kind of a little bit of a harsh way of looking at things, but it really is the underlying question that we worry about and that software developers should be worried about is how to keep the software going without a single source of funding necessarily supporting it. Support, I think here means if you have a piece of software, can I build your software and run it on my current system, and will I be able to do the same on a future system? Do I understand exactly what the software does? Is there documentation that helps me? Does it do what it's supposed to do correctly? And so is it verifiable? Does it do what I want? Does it have the functionality that I want today? And as my needs and my science needs change over time, is the software going to be able to change to address those new needs? And does it include the newest science? So if I can tell you that I have a particular algorithm that really works well for a particular science problem, can that algorithm be brought in to the software? So part of this also is a governance model. Right? So how does the software actually get run? The governance model tells users and contributors how the project makes decisions and how they can be involved, and ideally it makes them want to be involved. The community here, again, could be users, it could be developers, it could be people that just think the software is really cool and they want to be involved in it for some reason, and they might work on documentation or tutorials or things like that. There's a couple of different models for governance. There's the kind of benevolent dictatorship model that the Linux kernel goes through. There's a meritocracy model that the Apache process goes through, and there's probably other models. So I think the questions that a software development project needs to think about are what's going to happen in terms of sustainability and what's going to happen in terms of governance. And I should mention, the governance models I think can be tied to development models. And there's a nice paper called The Cathedral and the Bazaar from roughly '97 that talks about a couple of these different models. So finally, just to close with some general questions that we're thinking about, and I encourage other people to think about and to discuss, and maybe we can get back to this if you have interesting ideas. I think one is how does the open source model work for all science? So I think the open source model can work for all science. But it's questionable how it works for all science, particularly for smaller areas where there are smaller communities. I think for underlying tools, we clearly have many more successes. So the question, I think, is how many users or developers are really needed to make a successful open source project? And how true is the notion of open source? Is it really just open source for understanding, meaning people can look at the code to understand what it does? Or is it open source for reuse and development, which means that the code really is written in such a way that people want to work on it and want to reuse it? Software that's intended to be infrastructure has challenges from software that's just intended to be used for somebody's research. The more users you have using your software, the more work you have to do, and you often aren't going to get supported well for that work. And in the last 20% of making something really reusable and making it infrastructure may take 80% of the effort of the overall project. It takes some large multiple of the effort of just building it the first time through you. We have to think about what fraction of funds we should be using to support new existing infrastructure versus developing new infrastructure. So if we take the model that we support new projects and those projects stay up over time, unless our budget is increasing dramatically, at some point we'll stop doing new things and we'll just all be entirely supporting the existing projects. So somewhere we also have to figure out how do we stop supporting an element of software. Overall, how do we encourage reuse and discourage duplication? How do we avoid the situation where people redevelop something where there's already a model because that's what the funding policies encourage? And then finally, how do we support career paths for software developers? Again, within universities, within labs. The thing that industry does really well and the research community doesn't do as well at this point. So that's all that I was going to say. Hopefully this all has still come across and I can try to answer questions. People have them and the technology works, or people can email questions at any time and I'll try to get back to you. Okay, thank you.
Thanks very much, Dan. We do have time for a couple of questions before transitioning to the talk by Cheryl. So questions from the audience, since we're using this cyber infrastructure tool and environment. So if you ask, I'll repeat your question in the interest of time. because we have a microphone here. Yes, Sushil.
So question to Dan, the last thing that we talked about in terms of, what happens when the NSF funds really stop, and how the software really gets supported later on. So how do you actually support in future? What is the model that, that could work? Is it actually always going to be open software? Or do you see this to be patented or, put it out on the market? How does it, what is the most favorite in terms of, NSF?
Dan, let me repeat the question. The question was from Sushil, Georgia State. So his question is about sustaining support for future software evolution once the software start existing. So there are a couple of options his question was alluded to, such as what you mentioned through open source or as technology transfer or other mechanisms, what roles NSF is playing in this space.
Right, so I guess I would say that NSF, I think that a lot of these things move beyond the role that NSF is playing. So NSF's role is, ideally, is to support these things starting out and to support them over some period of time. But as I was saying, we can't support everything forever. So there has to be some way that projects, at least some projects, move out from just being NSF supported. It could be that the support is broadened and that there are multiple agencies supporting different parts of the project. It could be that there's some, again, some open source models, some business models that comes through. I think that those questions, actually, and I guess maybe one other option is it could be something that the university chooses to support, because it's really important for the university's reputation to have the software available. So we will support some things over a long time. The SI2 program in particular really makes the effort to support things that haven't been supported and to make sure they're available. But in order for us to do as much as possible, there really has to be other mechanisms for support besides just us. And so it's really something that we look at in terms of the projects that we fund, is what's going to happen after the 3-year or 5-year project ends. What are the PIs planning to do? In some cases, it might be that they're going to ask NSF for more money. And if it's something that's really kind of one of the most essential projects, maybe that's a reasonable answer. But it can't be the answer for everything.
Thanks, Dan. Additional questions from the audience?
Sure.
Yes, Steve. Oh.
Has NSF funded a study to look at the details of such an issue, since it's so important?
Question from Tim, local here, Washington, Seattle. The question was, has NSF funded any study looking to the issue of sustainable software support?
So I think NSF has actually funded a number of studies, some of which are overlapping in some ways. I'm not sure that there's any one that I can point you to. There's a number of eager awards that have done things like this. The Virtual Organizations Program, the VOS program, Virtual Organizations as Social Science, I believe, have done a number of studies like this. There's the Science of Science Policy program that really has looked at a number of issues around this. And then there's really the questions around, the much larger groups of people that have looked at this from people in the Apache Foundation, the Mozilla Foundation, the Sloan and Moore Foundations as other funding agencies also are quite interested in this. So I think we actually have a pretty large number of studies. It's just not clear that they're really pointing to any consistent single answers. It seems like there's a lot of different answers that work for different projects.
Thanks, Dan. Question from Steve? Okay, all right. Well, I have a question, Dan. So I was thinking about if there's any impact because of the change of OCI to ACI as part of SISE in terms of future solicitations and the plans with regard to the CIF 21.
So that's a somewhat of a political question that I'm not really able to predict what's going to happen in the future, and what the different people who are going to be leading both ACI and CIGIS in the future are going to do. I can say that the people that are leading the organizations now don't see a significant change occurring, and that in terms of the SI2 program in particular, the way that I treat the rest of SIGIS, the other directorates of SIGIS, is really just the same as I would treat any other science area. So for me, computer science is one of many disciplines we need to support, but we have funding to support all disciplines, and we try to support them all fairly. So I think in the short term, I don't actually see many changes coming. In the long term, it's really hard to predict.
Well, many thanks, Dan, again. Hope you enjoy your time at Michigan, and we really appreciate your time and flexibility.